I was just thinking about what I can say about someone I've known as a friend and a colleague for 35 years. And I thought back to the day that I met Bob, which was almost exactly 35 years ago. He probably doesn't remember, but I do, because he was busy making a sort of secret transition to Harvard as a tenured faculty member, and I was trying to decide where to go to graduate school. And so Bob doesn't know, but he actually recruited me to Harvard, even though he was a professor at the University of Michigan at the time, because he was coming to Harvard. And I'm sorry, Bob, but in awe of your work and your communication style, even then. And I guess I'm not sorry, I still am now. And at that time, Bob had just recently discovered something called the void in Boötes. And when I say communication style, I mean in his writing as well as in his speaking, which you'll get to hear today. And I just want to read you a sentence from the incredibly short abstract of this paper that discovered the first really gigantic void in space that led to later what Margaret Geller and John Hucker did to find this sort of bubbly structure in the universe. So they found the first bubble. And the concluding sentence of that says, one plausible interpretation of finding only one redshift of, by the way, there were 133 galaxies in this survey, which for those of you who are astronomers is amazingly small number. But anyway, so one of those 133 redshifts was where the peak of the distribution should have been, and instead there was a giant gap, and that was a void. And he wrote, one plausible interpretation is that a large volume in this region of order 1 million cubic megaparsecs is nearly devoid of galaxies. So this is like a great understatement. Like, we've just discovered the greatest hole in the universe, and okay, maybe it's devoid of galaxies. Okay, so Bob went on to do a lot with supernovae, which is something he's very fond of. He was very important in the study of supernova 1987A. Again, those of you interested in astronomy might remember that. But what he did that he's going to talk about today is something called supernova cosmology, where you use supernovae as a way to measure very accurately the expansion of the universe. And he's going to explain that to you. And he's going to explain, I'm sorry to steal his punchline, that they went out to look for the deceleration of the universe. And let me just say, I already hinted what, but something else happened. And the reason I mention this is because many of you have come to the other events in this series, the Undiscovered, this year at Radcliffe. And I just want to say that Bob's work and Chris Bowler's work, Chris Bowler, who's over here somewhere, I can't see him, there he is, Chris, who was a Radcliffe Fellow with me in 2016, 2017, and Stuart Firestein's work, who you heard from back in October at the Undiscovered, were the three pillars of the kind of inspiration of the Undiscovered. So the story is that Stuart Firestein talks about ignorance and how the interesting parts of science are the parts that are not in the book. And Chris Bowler came along and said, how about this Tara ship that I work on, which some of you had the privilege of seeing in Boston Harbor back in October, that does things like go out and sequence all of the plankton in the ocean and more than 10 times increase the number of known plankton in the ocean by just sequencing them. And those are examples, that kind of science is an example of where you have very expert people knowing exactly what they're doing, and then they're surprised by their results. So we don't want to give the idea that undiscovered means just pure serendipity. It means when a team of scientists or a scientist is very prepared to do something, and then maybe accidentally find something very different. And I'll let Bob explain why his story, which I've told some of you briefly in previous introductions to these events, is such a perfect example of an undiscovery. And I should give a proper introduction and tell you that Bob was an undergraduate here at Harvard, that he went to graduate school at Caltech, that I already mentioned he was a professor at Michigan, and then here at Harvard for 30 years. And now he's actually in charge of the science program at the Moore Foundation, the Gordon and Betty Moore Foundation in California, which he tells us is why he's wearing such a nice suit. It's a lovely suit, Bob. Anyway, I should cover up my dirty shirt here. Okay. Anyway, so he also has won many, many prizes, and that's why I have to look down because I listed just a few so that I don't forget them. The Danny Heinemann Prize in Astrophysics, that was after winning the Caltech Distinguished Alumni Award, the James Craig Watson Medal, and the Wolf Prize in Physics. But I hope he remembers that my favorite award that we gave him was the year after he discovered what he's going to tell you today. He remembers, he says, the shirt. Yeah, so we gave him a T-shirt on the occasion of his 50th birthday that said, The universe isn't accelerating, you're just slowing down. So I would stop there, but I just have to read you one email that I got this morning. So Bob and I and the other astronomers in the audience get many, many emails from high school students and students all over the world all the time. And just this morning, I got this message, which Bob is going to now answer for you. It says, "Hello, my name is Carson, and I am a sophomore at Jefferson Forest High School in Lynchburg, Virginia. I am very fascinated by astronomy, and I have a question. If space is infinite, then how is it always expanding? I have been wondering about this for a while now, and the astronomy teacher here was unsure of the answer, so I went to a Harvard professor. I understand you are extremely busy, so just get back to me when you can." So Carson, another Harvard professor, who, by the way, points out that in addition to his appointment at the Moore Foundation, he is still a research professor at Harvard, which is free to Harvard, so happy for funders. Anyway, so Professor Bob Kirshner will now explain to us the expansion of the universe and its extravagance. So thank you, Bob.
All right, thank you. Oh, me. Well, thank you very much. It's great that you have taken the effort to come here, and I'm very pleased to be here myself. I'm going to try to stick to this idea of not discovering the thing we set out to find. We set out to find the deceleration, the slowing down of the expansion of the universe. And as I'll show you, we found something else. So let's start. As Alyssa has said, I'm a Chief Program Officer at the Gordon and Betty Moore Foundation. Gordon Moore was the head of Intel, and that was the source of his money doubling every 18 months. And so he set up a philanthropic foundation. I'll show you the plot later. And I'm still the Clowes Research Professor of Science. That means that Harvard doesn't pay me. I don't teach, but they collect overhead on my research grants. This is, from the point of view of a university administrator, just about perfect. And I don't need an office anymore. So there you are. All right, well, let's start. You can't go wrong with looking back to Galileo. And here's Galileo in Venice showing off his telescope in front of the Doge's palace. Galileo said, "All truths are easy to understand once they are discovered. The point is to discover them." So to give you one example of what Galileo did with that telescope was to take a look at the moon and to realize that the moon is a real place with mountains and pits and what they thought were seas, that it is a part of the world made of the same stuff, he thought, as we are, which was somewhat at variance with the view that there were sort of four essences, and then the astronomical thing, the fifth essence, the quintessence. So here I show you air. Easy to show you air, an empty glass. Is that glass half empty or full of air? Water, fire, and earth. And then the fifth essence, there are five shown here, is the black frame, okay? And we're going to come back to something sort of in the background that is really very important to the structure of the universe. Now, the idea that we can tell what the world is made of comes from astronomy of a couple hundred years ago, where you take an object like the sun, and if you pass it through a prism or use another kind of instrument to do it, you can spread the light out into a spectrum. So you know what a scientist's job is. It's to take something beautiful, the rainbow, and to turn it into a graph. And that's what you see here. Up at the top is a graph that shows as up and down where the light is bright and where it's dim. And you'll notice, it's even more conspicuous in the illustration down at the bottom, that there are these lines that go across the spectrum. Those are certain wavelengths or colors, energies of light, where the light is absorbed. And it's absorbed by the atoms in the atmosphere of the star. like that one that's in the yellow out there. There's a nice sharp yellow line. That's caused by sodium. The element sodium absorbs the light, and that's how we know what the sun is made of. The sun is made of mostly hydrogen gas. That was something which was not obvious at the beginning, but was worked out by a very good graduate student here at Harvard, Cecilia Payne-Gaposchkin. The other things that you see here are elements that we know from the periodic table. Those are the familiar elements, and in fact, most of the elements that you know about from chemistry are also observed in the stars. And we'll come back to another use of the spectra in a minute. So I want to start about 100 years ago. Everybody knows that on a clear summer night, if you get out from the city, you can see the band of the Milky Way across the northern sky. And this is a representation of our own galaxy, the Milky Way galaxy, which, of course, no one could actually see it all at once. This is a picture that's stitched together of what you would see from the northern hemisphere and what you would see from the southern hemisphere. You can't be in two places at once. But this gives you the idea. It's a big flattened disk, bulge in the middle, lanes of dust throughout. And what I want to emphasize in this picture, well, first is the idea that 100 years ago, astronomers thought that the Milky Way was basically the whole universe. And as we know now, there was a big change in our point of view, and I'll talk about where that came from. So the most important thing in each of these pictures, like that dark background in the four elements, the most important thing is kind of invisible or in the background. And here, the most important thing in this picture, for this story anyway, is that little fuzzy thing, a little nebula, which is the Andromeda Nebula that we'll come back to in a minute. Well, all right, 100 years ago, there was also very strong advances in theoretical science. Here is Albert Einstein, sort of known to everybody, and he's thinking about the nature of the universe. You'll notice something interesting about the technology here. This is taken with a photographic plate. That's a thing that has a chemical reaction between light. Well, the light produces a state of a silver salt that you can then reduce to silver metal and make a negative, do all that stuff with chemistry. And one thing about it is it's a lot less sensitive to light than the electronic camera that's in your cell phone. And I'll come back to that revolution in a minute. And you can see it right here because there was somebody seated in this chair who did not wish to be photographed with Einstein, and the person behind him disagrees with him and is shaking his head. The shutter is open for quite a long time. The big advance is that we now can look at these photographs and see what people were thinking. And what Einstein was thinking was that the universe, this Milky Way that we were talking about, must be static. He had just invented general relativity, the theory of gravity that tells how things pull on one another, or really how the presence of matter curves space and objects move through space. And Einstein was a very creative thinker, and he thought, well, how could I apply this to the universe as a whole? Well, of course, universe meant the Milky Way, so he knew that the Milky Way didn't seem to be expanding or contracting. So he thought the universe must be static, and he put in by hand an extra term into his cosmology equations, or the gravity equations, to make the universe static. And he said, can you read this from the back? Yes? No? Oh, too bad, because I was going to say I was translating from the German. It says, that term is necessary. I'm going to do it later. That term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So at least when he wrote the paper, he was thinking in this very empirical way that he somehow had to solve a problem and make it so the universe was static. Okay, who broke this problem wide open? Well, it took a lot of people, but one of the people at the beginning is Henrietta Swan Leavitt, who worked at the Harvard College Observatory She lived on Garden Street in the place where the Curious George house is, and worked at the observatory for 25 cents an hour. But the observatory director only got $3 an hour. You listen to this, everyone? You know, $3 an hour. And she noticed that when you studied a certain set of stars that were all at the same distance, that she could tell that these stars, which were vibrating, getting brighter and dimmer, that the ones that were brighter had longer periods. That is, it took longer for them to get bright and dim. Just like a big bell takes long and has a lower note than a little bell, the big stars, the luminous stars, had a longer period of vibration. And that turned out to be very important because in astronomy, we're always getting confused about what's nearby and what's far away. You look at two stars and you don't know whether you're looking at a firefly that's in the foreground or a star 100 light years away in the background, until you can sort out what those objects really are. And the observatory director, who was earning this princely sum, here he is, Harlow Shapley, used the variable stars to try to map out the Milky Way. And he showed that we don't live in the center of the Milky Way. We live out in the suburbs. And something like this. Now, this is not a picture of our galaxy. The students are onto this. Because, of course, we have no way to get outside. The best we could do is that sort of edge-on picture that I showed you earlier. And it turns out Cambridge is not actually the hub of the universe. It is somewhat out in the outskirts. Okay, so I'm going to emphasize instruments. I talked already for a second about photography. And of course, one of the things that changed this subject of how to use those variable stars and how to map out the structure, the distances in the universe, was the invention of big telescopes. So here's a big telescope. That's the 100-inch, that's the diameter of the mirror, telescope at Mount Wilson, which is up above Pasadena in California. So that telescope was built in this same era that I'm talking about, nearly 100 years ago, about 100 years ago. And it was used to measure stars, the same kinds of stars that Henrietta Leavitt had been talking about, in other nebulae to see how far away they were. So again, the most important thing in the picture is kind of inconspicuous. It's the chair. The chair is where the astronomer sits and uses a big photographic plate to take an image of a galaxy. And by taking pictures night after night, Edwin Hubble, who used this telescope, was able to search for the same kind of variable stars in the Andromeda Nebula, the thing I pointed out a few minutes ago, for the same kinds of stars that Henrietta Leavitt had seen more nearby. And so here's a very famous picture that he took with that telescope in October of 1923. And you can see there's the fuzzy thing in the middle, so it's sort of like the picture I showed you before. And he's marked up on the upper right a particular star, and he was looking for stars that changed, that got bright, novae. But he realized after looking at this plate and the ones he had before that it wasn't just a new star, it was one he had seen before, that it was a variable. And it was a variable of the type that turns out to be the same as the type that Henrietta Leavitt had seen, only it was a lot dimmer. Well, that means it was a lot farther away. If you look out, over a desert landscape and there are cars out there, the ones that are nearby look bright, the ones that are distant look faint. And what he found was that the distances in the two galaxies were much bigger than the distance across our own Milky Way. So Shapley was very impressed with how big the Milky Way was, and he thought those nebulae were just some little things at the edge. But the distances we measure in units of the time it takes light to get from one place to another. The unit of distance we have, a foot is the distance that light travels in a nanosecond, in a billionth of a second. A foot is used in the United States and in Liberia as a unit of distance. The distances of the stars that you see when you go out tonight, well, not tonight, but on a clear night, might be 100 or 1,000 light years. That means the light took 100 or 1,000 years to get here. The diameter of the Milky Way is something like 100,000 light years. But what Hubble found was these stars, which were the same kinds of stars, but hundreds of times fainter, must be 10 times as far away, roughly speaking, millions of light years away. So this really was a big surprise then, that the universe was a much bigger place than people had thought. Well, what about Einstein? Well, Einstein, here you see a picture of Einstein at the Mount Wilson Observatory. That's Hubble hovering over his shoulder. And that guy looking really worried is the observatory director, because he is afraid that this theorist is going to somehow damage the instrument. Now, if so the universe is much bigger than people thought in 1915, let's say. But there's something else, and that is that you can tell from the spectrum that I talked about before, the thing that lets you see what chemicals are in the atmosphere of a star, you can tell whether things are coming toward you or away from you. There's a shift in the wavelength, the color of the light that's due to objects approaching that look bluer, objects that are receding look redder. We know this from sound. Everybody knows the sound of a car going by. It goes from a high pitch to a low pitch as it goes past you. And if the speed of light were 1,000,000 times lower, highways would look like this. The cars coming toward you would have blue lights on the front, and the cars going away from you would have red lights. Oh, they do. Well, okay, that's for a different reason. But anyway, the idea is you can tell whether things are coming or going. Here is a fellow called Vesto Melvin Slipher at the Lowell Observatory, and he's using an instrument, one of these devices that takes the spectra of stars, of galaxies, and he was measuring the velocities of the galaxies. And what he found was something really weird. He found that there are a few coming, and but almost all the galaxies that he measured, and he measured a couple of hands full, were moving away from us. That's kind of strange. So Hubble was measuring distances to galaxies. Slipher was measuring velocities. Now, many of you know where this is going. Hubble is famous for Hubble's Law, which relates the velocities and the distances. And in 1925, Hubble had all the information he needed to make the diagram that shows that we live in an expanding universe. Why didn't he do it? Well, it turns out he wrote that in his book. In the book, The Realm of the Nebulae, which he wrote later, he said, it was natural inertia. Students, pay attention. If, for example, an assignment is overdue, what is the correct thing to say? Natural inertia. It was natural inertia in the face of revolutionary ideas, that's the general relativity, couched in the unfamiliar language of general relativity, discouraged immediate investigation. When he's talking about himself, he always uses the passive voice. He says, discouraged immediate investigation. So here's the diagram that in 1929 he finally got around to making, where you plot, you know what scientists will do, you get two lists of numbers, you plot one against the other, you make a graph, here's velocity against distance, and you can see that there's some relation between them. The things that have small distances have small velocities. In fact, a few of them are coming toward us, which was very puzzling to people later. As you go farther out, you're looking at objects that are moving away from us. So it isn't a static universe. This cosmological constant that Einstein put in by hand into his general relativity equations was something that he discovered 10 years later he didn't really need. So here are the players in the game. Here's Einstein. He's next to the observatory director, now in his good suit, still smoking a pipe, though. And over here's Edwin Hubble. And here's Humason, his assistant, who actually measured a lot of these spectra. And George Ellery Hale, who is the man who was responsible for building the 100-inch telescope, is up on the wall. He's patting Hubble on the head. Good work. Okay, so if the universe is not static, then you don't need the cosmological constant. And if you look in the literature, or the writing about it, people say, well, Einstein called it his greatest blunder. And I got really interested and tried to track down where he said it. Turns out one place where somebody says it pretty clearly is George Gamow, who's a notoriously unreliable witness. But in his autobiography, which was written by him, only he could write that, he says, Einstein's original gravity equation was correct, and changing it, putting in the cosmological constant, was a mistake. Much later, when I was discussing cosmological problems with Einstein, I really wanted to put that in my book, but couldn't do it. Much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder he ever made in his life. But this blunder, rejected by Einstein, is still sometimes used by cosmologists even today. And the cosmological constant, denoted by the Greek letter lambda, rears its ugly head again and again and again. George, calm down. Okay, so that's my story, is going to be that we thought we were going to measure a universe that was slowing down due to gravity, but the cosmological constant has reared its ugly head again, only this time with evidence. All right, so let me say a little bit more about that. We live in an expanding universe. You may be a bit puzzled, and in fact, the student who wrote in is clearly a little bit puzzled about this. The view that my experience has been that most faculty at Harvard have is that they personally are the center of the universe, and it's also true for undergraduates. Well, anyway, that many people think, well, it's you that's at the center, but no. If you have a universe that's stretching out in all directions, if you imagine this, then in fact, your neighbors will be moving away from you, and the ones who are more distant neighbors will be moving away from you faster. If I could have the power vested in me by the Reverend Board of Overseers to double the size of this room, the person who's sitting next to you would end up 2 seats away. The person who was 2 seats away would end up 4 seats away, moving away twice as fast. The person who was 4 seats away would end up 8. What you would see is exactly what we see in the universe that we actually live in, Hubble's law. Okay, so when we see a bunch of galaxies out there, and we measure the velocities, we can use that to understand how the universe is expanding. That's the point of all this. Well, what about the cosmological constant? At first, people thought, well, that's what makes the universe expand. And so you can see here a cartoon from a popular publication in the Netherlands that says, it shows a person, that is Willem de Sitter, in the shape of the Greek letter lambda, get it? And you can see that that's making the universe swell up. You can read the Dutch because English is a dialect of Frisian. It says, something the ball up? What makes the universe expand or swell up? That's got to be lambda. No other answer can be given. Pretty good. But they gave up on it very quickly because Einstein said, no, you don't need lambda, so let's get rid of it. And after that, this is Sitter and Einstein discussing this matter, discussing something. And they basically said, that cosmological constant, which we put in to make the universe static, is a bad idea. Let's get rid of it. So I was in Washington over the weekend at the National Academy meeting. Here's Einstein. Well, it's not Einstein. It's a statue of Einstein. And he's holding a tablet, which he brought down. Well, not really, he wrote on. And here are some equations on here. So, serious talk has to have equations. And here you see an equation that you recognize, E equals mc squared. That has something to do with the generation of energy in stars, how mass can be converted to energy. That was too far out for the Nobel Prize Committee. But the one above, they understood pretty well. This is about the photoelectric effect. I was talking about chemistry for detecting light. This is how you can measure light by its physical interaction. The light comes in and it kicks out an electron. And up at the top is the equation, basic equation for general relativity, and there's no lambda in it, okay? There's no lambda in it, at least there. So basically, by about 1930, people had stopped talking about the cosmological constant. Einstein and De Sitter had made up a kind of universe where gravity was the dominant thing, and it would slow down the expansion of the universe as a whole. And people thought that what they ought to do is go out and measure that. Now, there were some heretics. I always like to show, a clerical heretic. Here's Georges Lemaitre, who was a Belgian priest who came to study at Harvard, but Harvard did not give out the PhD. That was thought to be too Germanic at the time he was here. So he enrolled in MIT, even though he was working with people at the Harvard College Observatory. And he had some really profound insight into this. He said, well, everything happens as though there's an energy in the vacuum that's not zero. And that the cosmological constant, this is a very modern way of talking about it, that the cosmological constant is a way of thinking about the energy associated with gravity in the vacuum. And he says this essentially is the meaning of the cosmical constant lambda. Okay, so Einstein really gave up on it. Here's a famous postcard he wrote to Weil, a mathematician. It's in German, and it says here at the bottom, if we live in a quasi-static world, then away with the cosmological constant. That's basically what it says. Go quickly, because you don't know what you're talking about. Okay, here we are. So we have a universe that's expanding. It has possibly this model that Einstein and De Sitter had thought about, where the universe would expand but slow down over time. One other thing that's really interesting that you can get from the measurements of the motions of the galaxies is that they're not only expanding with the rest of the universe, but they're moving with respect to each other, and the stars in them are moving around because of the force of gravity. And here's Fritz Zwicky, who was a pioneer of dark energy, a pioneer of supernova explosions, that I'm going to be talking about in a minute, and a pioneer of rude gestures. It turns out that he referred to his colleagues at Caltech as spherical bastards, he'd say. They're bastards any way you look at them. But what Zwicky saw was that if you looked at the motions of galaxies with respect to one another in a big cluster of galaxies, that there was more mass there than you could account for by the stars. He thought there had to be extra mass, which was dark, which he called the dark matter. And today, that's how we think about the clusters of galaxies, where here you see not only these big yellow things are the galaxies, but gravitation is actually warping the light from behind the galaxies. There's some things in the background making those beautiful arcs that you see. And those are a signature of the presence of extra mass. We also know from X-ray observations of the hot gas that's in clusters that this is real, that there's a lot more mass in galaxy clusters than you have accounted for by the stars. It's also true on the scale of individual galaxies. Vera Rubin, who worked very hard on measuring the motions inside galaxies, showed that they are in orbits, the stars in them are in orbits that require much more mass than you would have from the luminous stuff that you see. So this idea that the universe has dark matter in it was part of the story of kind of figuring out, well, you'd like to find out how much dark matter there is. One way to find out would be to look at this expansion and to see it slowing down. So that became something we all wanted to try to do. Here's a radio observation of a galaxy, in fact, the same one I showed you a minute ago. And it's been encoded so that the radio emission, which is shifted to the longer wavelengths, is shown in red, and to shorter wavelengths in the blue. And you can see that this galaxy is rotating. The one side's coming toward you while the other side is going away. So we know that this is true for galaxies and clusters of galaxies, that the universe is got a lot of stuff that we don't see. How do you understand this? Well, so what we see are the stars, and what it's telling you about is the dark matter that's inside them, inside the galaxies. So it's always good to slow down and go to the art museum. And here you see something which tells you a similar story, which is when you look at a mountain range in the moonlight, what do you see? You see the reflected light from the snow that's on the mountain range. But that is not the mountain. The mountain is the stuff under the snow. And in the same way, what you see is the light from the stars, but most of the mass is not visible to you. It's the dark matter. And here is a bad haiku. Deep snow traces rock. Always winter, never spring. Mountains do not melt. Huh? Bad, but mine. Okay. So that's the idea. The visible matter traces the dark universe, and if we want to see the history of the universe, we should look at that stuff. Look at the effect of that stuff. So you might ask yourself, well, all right, if this is real, why can't we measure it? I mean, in the laboratory, here on Earth, if it's in our galaxy, the Earth is going around the center of our galaxy, we ought to be in a kind of fog of this dark matter, and it ought to come whizzing in the front, and we ought to be able somehow to figure out how to detect it. People have tried to do that. Let me just say, you don't necessarily expect the results to come in immediately. You may be waiting in the rain for quite a long time. Astronomers knew that the speed of light was finite in the 1600s, and it took 150 years before you could make a laboratory measurement to measure the speed of light, because it's very fast. A foot in a nanosecond, and they didn't have clocks that were good to a nanosecond. You had to figure out a very clever way to do the timing. It was done at the Paris Observatory. So the same thing for the dark matter. People have been very clever, and we've known pretty well that there is dark matter since about 1933. And if you read the literature, everybody who works in this field expects to see it next week. Isn't that right? So here's and they never do, or they haven't done yet. So here's a particular experiment, a jug of xenon in a mine underground to get away from cosmic rays, and no dark matter seen yet. Okay, but you could at least measure how much there is if you could measure the slowing down of the universe. So here's something, dark matter now has a day, Dark Matter Day. Their slogan is, don't be afraid of the dark. And I think it's the day before Halloween or some other symbolic day. Anyway, how to measure the cosmic deceleration. So here's where the supernovae come in. I talked about measuring distances with the Cepheid variable stars. If you want to measure the cosmic deceleration, you've got to measure it over a much longer distance. You need a much brighter thing to do that. And it turns out the supernovae are 1 million times brighter than the stars that Henrietta Leavitt was studying. I'll show you one in a second. And you can see them 1,000 times as far away. So Hubble was measuring distances of millions of light years. 1,000 times a million is 1 billion. So you can measure the distances over billions of light years. And it turns out that's enough to be able to see the subtle effect of gravitational slowing down. It would be enough to see the subtle effect of gravitational slowing down if you had enough of these objects. Hubble knew about supernovae. He said, supernovae can be detected at immense distances, And in principle, they are a criterion of distance about as reliable as that of total luminosities of the nebulae. That's what he was using to measure distances. Actually, however, he was from Missouri, but he went to Oxford as a Rhodes Scholar, and he came back saying things like, actually, forever. Actually, however, the maxima are so seldom observed, and the supernovae themselves are so rare that they contribute very little to the present problem. He was right. They were really hard to find using the old technology, using the photographic plates and things that people had available to them at the time. Okay, there have been supernovae in our own galaxy. Well, here's a picture of a supernova in a galaxy. You can see it's quite a bright thing. And as Hubble says, they're about as reliable as the luminosities of the nebulae. Here's one in our own galaxy. If there's everywhere in the universe, they ought to be in our galaxy. This is taken with an iPhone of Tycho Brahe at his fanciful etching of his Uraniborg castle in Denmark. And you can see somewhere up there in the constellation of Cassiopeia, that spot, which was the site of a new star, which we know now was a supernova in 1572. So there have been these things in our galaxy. We can study the nearby ones. If you go now and you look with radio telescopes and X-ray telescopes and optical telescopes at that site, here's what you see. You see a beautiful wrecked star that is the green fluffy stuff is the interior of the star. It's all moving outward. There's a bright rim that's due to the radio emission where particles are accelerated to nearly the speed of light. This is the remnant of Tycho's supernova. And we can still see it now, 400 years later. All right, so we know about what these phenomena are a little bit. They're beautiful things. And they lead us to beautiful ideas because they allow us to see what the universe is made of. So here's another supernova in a galaxy. If you take the velocity of the galaxy by measuring its spectrum, and you infer the distance from the apparent brightness of the supernova, you can make a plot like the one that Hubble did, and here it is. This is early days in our work on supernovae, but anyway, it's a pretty good diagram. One thing that's kind of fun about it is that you see that little red square down there in the corner. That's where Hubble's Hubble diagram was, the one that I showed you 20 minutes ago. And what we're seeing is that the supernovae make a nice linear relation of velocity and distance over a much bigger distance, out to 1 billion light years or so. Okay, so what if you could measure 2 billion or 3 billion or 4 billion years into the past? Could you see the signature of this slowing down? And the answer is, yeah, if you got enough of them and you did a good enough job. So here in 1995, my colleagues and I wrote a telescope proposal. You have to write in and say why they should give you the telescope instead of somebody else. And what you see is this line of the linear Hubble expansion. It's not obvious enough. We write out linear Hubble expansion. And then as you see, if you go to the far side of this diagram, that those lines diverge. Those are different possibilities for the universe. Slowing down a lot, slowing down a little, slowing down not at all. And the upper ones are things that would speed up, but of course that would require a cosmological constant. And Einstein told us that was a terrible, terrible idea and we shouldn't think about it at all. So we didn't. What about the technology? Well, here's my thesis advisor in the 1990s, and he is holding one of the world's largest digital devices, a CCD at the time, a CCD that had 0.24 megapixels. You can't even buy one that's that small anymore. And of course, it's the advance of technology that I alluded to earlier that has made it so these chips, which are fabricated exactly the way computer chips are fabricated, they're made of the same materials, the same kinds of techniques are used, has really advanced. In fact, Moore's law, Gordon Moore of the Gordon and Betty Moore Foundation, is the relation between the number of transistors on a chip and time. And you can see for this that it's been going up really fast. This is on a kind of scale where the separation is a factor of 10. You can see it's 1,000, 10,000, 100,000, a million, 10 million, going on up. Interestingly enough, Moore's law that has led to the incredible change in our ability to do computational work also had an interesting effect on Gordon Moore. And at about 2000, he got into the zone where he had billions of dollars, and he thought, I don't need any more. And so he set up the foundation, the philanthropic foundation that I work at. So that was a good thing. The change from itty-bitty detectors to great big ones was really important. Here's a picture of John Tonry, one of our colleagues. And as I mentioned, I was at the National Academy over the weekend. John was inducted into the National Academy. He's a Harvard graduate. And here's how we got going using those bigger detectors. The problem is, how do you make that measurement and find the supernovae to do the job that I was talking about? So here's someone, that's what I used to look like, and I'm with Brian Schmidt, who was a graduate student, and here he is explaining how easy it's going to be to write the computer code to take a digital image and take another digital image, subtract them, and find the new object. So that's how it works. You take a picture, so Epoch 1 might be a month ago, and here's Epoch 2. Well, if you look at those two pictures, you have a hard time telling if there's a new object there, but if you take the subtraction of the two, it's pretty good, and there's a nice red circle around it. This is about 1/1000th of the image area of the detectors that we actually used. If you had to do this 1,000 times that, times 10 fields every night, the graduate students wouldn't do it. And so Brian Schmidt is not a lazy person, but he said, I'm going to write some code and make this happen. So this is sort of the beginning of big data in astronomy. Well, it's not really all that big anymore, but we thought it was big data. Now, to be fair, there was another group in the field. So that's Brian in the shorts, and that's Saul Perlmutter, who led a group at the Lawrence Berkeley Lab that was doing something similar. And you can see that there was a friendly competition between them. Well, they were trying to do something very similar. And in 1997, I thought the game was over, that they had beat us, and that they had discovered cosmic deceleration. So there's a paper, it's in the Astrophysical Journal, where they say that the universe, this omega matter, is nearly 1. That means the universe has the density to slow it down in the way Einstein and De Sitter were talking about. For a lambda equals 0 cosmology, no cosmological constant. And it says the results are inconsistent with lambda-dominated, a cosmological constant, low-density, flat cosmologies that have been proposed to reconcile the ages of globular cluster stars with higher Hubble constant values. That last line is exactly what we think is the correct answer. Okay? It's not, well, the data they had were inconsistent with that. And we were in the same game. Here's a paper from 1997 where Brian is the lead author. And it says, the High-Z supernova search, that's our name for ourselves, measuring cosmic deceleration. So that's my point, that's what we were looking for. We thought we'd been beaten to the punch. But, and this is the nadir of the talk. I mean, really, this is the worst. But it's going to get better very soon. Here's Adam Reiss, who was a graduate student. There's me in my vest. You wanted to see the vest? I got the vest. Okay. And Adam, who was a student at MIT, always kept a lab notebook. And we had a little bit of data. And it looked like in our data that when you did the analysis, this omega matter, the amount of matter in the universe, had to be negative, which sounded crazy. But it's what you would get if you analyzed without taking into account a cosmological constant. It's that instead of slowing down over time, it's speeding up over time. And so here's the evidence that we had back then, 1998. The blue dots are ours, the red dots are theirs. They have more, but bigger scatter. Well, there you go. And what you see is that we're trying to tell which of those lines is the right one. Down here, we've taken out the 45 degrees, and you can see that the horizontal line isn't the best fit. The points are more up above it. And this dashed line down here that curves downward, that's what you'd get in a decelerating universe. That is really not the right fit. And even without the powerful tools of statistical analysis, you can see that the points lie up above. That's where they'd be if the universe was accelerating over time. How do you think about this? Well, the supernova goes off, the light's coming toward you. If the universe is expanding, it takes time for the light to get to you, and there's a certain distance. If it's expanding faster, then it has to go farther, and it takes longer, and it's farther away and dimmer. So the signature was that the supernovae were a little bit dimmer. This was a big surprise to Einstein, as you can see here, although Einstein had been decomposing for some time. But the way we think about it is that there's a kind of tug of war between the dark matter and the dark energy. Dark matter trying to slow things down, dark energy trying to speed things up. In the early universe, the matter is ahead, and it slows things down, but it gets diluted over time. If the thing that's speeding things up is really the cosmological constant, it's constant, so even though the universe is getting bigger, the energy density of the cosmological constant is staying the same, the vacuum energy is staying the same. And that leads to a universe that will slow down for a while and then accelerate, and it looks like that's the kind of world we're in. So here's a kind of complicated looking diagram, but it shows how much dark energy and how much dark matter. Those are the points that we had back in 1998. Here's more or less where we are now. The thing we've done over the last 20 years is get more data. If you have a signal that is, kind of surprising, there'll be many people who will be skeptical of it, and that's a good thing. But if you get more data, and the signal gets stronger, that's a very good thing. And here, it's not only the supernova data, but data from studies of the cosmic microwave background, the glow from the Big Bang, the study of galaxy clustering, that all converge on an answer that looks like we have a universe that is mostly dark energy, partly dark matter, and just a pinch of the stuff that we're made of, just a pinch of the stuff that we're made of, ordinary matter. Now, this is a big deal. So I show you here a picture of Brian and Adam and me. We're in a hotel, but the hotel is in Stockholm. And then we put on our fancy suits, and Saul and Adam and Brian all won the Nobel Prize, and we stood around in our suits. So that's good. We have much better data now, and the evidence for acceleration has not gone away. You can't see it, but I can. That line is curved upward in the way the ones that have acceleration are. This bottom panel shows the difference between the model that we're talking about and the data, and you can see it's nice and flat. It's a little bit of noise, but pretty good. You could do this now. So here's a set of data of redshifts and distances, and the line that's ticking across is what you would predict for different amounts of the dark energy. And what you can see is if you have zero, it starts off at zero, and that's not a good fit. Ooh, that's better. One more time. So that's no good, no good, no good, no good. Keep going, keep going. Oh, it's getting better, 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 best. Too much. So you can actually measure how much of the acceleration there is, how much of the dark energy there is. All right, let me put this together. This, no more blunders. Never mind this. I've been working on this. Okay, So as I said, I'm now working in philanthropy, and so now I always think about money. And if you look on the back of the $1 bill, there's all kinds of mystic stuff, including this weirdo pyramid, in which the proportions, I've listed out the proportions about as the volume of the pyramid of what the world is made of. And it turns out that it's about 2/3 dark energy, this weird stuff that we just discovered 20 years ago. It's almost 1/3 dark matter, which is not the stuff of the periodic table. And the atoms that make up the intelligence, therefore with the gleaming eye that you see there, of the universe, the stars that we know about, the planets that we know about, all the things that we see glowing, it's just a tiny fraction of what's really there. And the history of the universe is determined by this unseen stuff, the dark matter and the dark energy. And the luminous stuff is sort of along for the ride. So we think we were in a universe that's been changing over time, slowing down at first and now speeding up. If you want to find out what the dark energy is, of course, in the old days, you could just Google it. And that was before all the institutions that had spent a lot of money on dark energy research put up their own websites that explained everything and made them seem like the discoverer. I mean, they did a good job on explaining it to everyone. In the old days, you could get this from American Hydroponics, which was it's plant food for growing marijuana in your closet. And it says, the specialized processes here are responsible for the very distinct odor of dark energy. Okay, so I've made it sound like we've got a new picture, and it's just great. And we do have a new picture, and it is just great, but we still don't know whether the dark energy is the cosmological constant or something else. The thing I kind of skipped over is work I'm doing now to try to measure that. But those of you who've been reading the newspapers and science things in the last week or so might have seen this. This is about the rate of expansion measured with the Hubble Space Telescope in the nearby universe compared to the distance to the scattering of the microwave background, and it doesn't quite fit. It's not quite what you'd get for the cosmological model I described so glibly, the one that has dark matter, dark energy, and a cosmological constant for the dark energy. So the wheel is still in spin. We do not know what the dark energy is, and we're going to find out either by a direct approach of making those measurements better, or perhaps by some of these slightly indirect ways. So the universe that we live in is a universe that is ruled, in a way, by the unseen things. So the mountain is not the snow. The snow is the thing on the surface. That's what we see, but there's a substance beneath it that is invisible to us. In the same way, the dark energy is not something we see, but we see the effects of it. So the artist here, of course, is trying to depict the wind. And you don't see the wind when you look outside. What you see is the tree moving because of the wind. And in the same way, we talk about the dark energy as accelerating the universe, as seeing the effect of it in the diagrams that I showed you. Okay, well, you may say, well, that seems like kind of a weird universe that's not the one I would make up. Well, you're right, of course. And here's a T-shirt that embodies that thought. Here's what it says. The universe is under no obligation to make sense, but students getting a PhD are. And apparently I said this somewhere. And it was on these T-shirts that were at an institution of research that had a gift shop. And you could go in and buy them. And so I went in there and I said, I am Robert P. Kirshner. And they said, oh, that's very good. They said, we'll give you a good discount. Okay, what kind of science is this? All right, you know, when I was president of the American Astronomical Society, I would stand shoulder to shoulder with heads of other learned groups, and we would talk to congressmen or philanthropists, and we would explain to them, what science was good for. And the arguments that go over big with Congress are to talk about technology, that is the economic benefit of science, to talk about defense, that if you don't understand the world well and have good detectors and powerful weapons and so on, it's a dangerous world out there. A lot of the congressmen are kind of old, so medicine is very popular with them. And so, in a way, they're asking us to promise that science will make everyone rich and safe and immortal. Well, I'm in favor of all those things, of course. But I think we do this work for a different reason. I think we do this work because we're curious. And if we were rich and safe and immortal and bored, that would not be an ideal world. And I think we have confidence that if people go out and do scientific research for the motive of finding out how the world works, that all those other things will come along with it. So I think doing scientific work for the joy of finding out how the world works is something that we should take care of, not forget, and now I'm in a position to help a little bit to make it happen. Thank you very much.
So I'm an astronomer, so I should know the answer to this question. But I didn't discover dark energy, so I'm going to ask you. So when the expansion of the universe was discovered back in Hubble's day, and Einstein suddenly decides, as we hear it, that the cosmological constant wasn't needed anymore, well, why is that the case? If everybody thought that the universe was static, and instead they found out that it's actually expanding, but at that time they didn't really know why it was expanding.
Right.
We didn't really understand the Big Bang. So why was he so quick to give up on the cosmological constant? Why didn't he just say, aha, the cosmological constant is pushing the universe apart? You alluded to it, but you didn't really answer.
I showed you that cartoon, and it's De Sitter, who is the person quoted by the newspaper, saying it's the cosmological constant that is making the universe expand. So that's just the right thing you said. And then, very shortly after that, Einstein and De Sitter got together and they wrote a paper that said, well, the legend is that Einstein said about this paper, which they wrote together, that said, forget about the cosmological constant, let's just use this model that not only doesn't just set it to zero, it just leaves it out entirely. The legend is that Einstein said, well, I never really liked that paper, but I did it because De Sitter wanted it. And De Sitter said, oh, I didn't really like that paper, but I did it because Einstein insisted. I think it's a good question. I think the fact that this has been rehabilitated and is now seen, looking back as the origin of the modern ideas, that's why I showed you the Lemaitre quote. That's totally different than what somebody would have done in 1990. In 1990, we all would have said, oh, cosmological constant, last refuge of scoundrels, terrible idea. Every time someone has brought it up, it's been, a bad idea. So I think we probably ought to do a little more homework on the question you're asking. What is the origin of the idea? How much did it fizzle out? Lemaitre, who still was talking about this, of course, went out of astronomy and into university administration. I'm not casting aspersions, but, and he was very influential in getting computing machines into the University of Louvain, where he was a dean. So, but he didn't have students, and he wasn't out there talking about this very much. But the idea didn't completely go away. So I think you raised a good point. Why did it go away? I think it was the authority of Einstein and De Sitter, and they said there's no reason, no theoretical reason to have this, so let's get rid of it. The thing that is the idea that's expressed in that postcard to Weil.
I read a paper about a week ago that they had discovered a second galaxy that lacked dark matter, like a signature of dark matter, and I was a bit confused by it because
Yeah, me too.
I thought that every galaxy was formed by dark matter, and so all of a sudden there's a second galaxy now that
Yeah.
looked all different.
Yeah, so that's a very good question. And of course, our knowledge of the dark matter for each individual galaxy is not very good. Most of them are not studied very thoroughly. But people have been looking at galaxies, especially galaxies, real little ones, these dwarf galaxies. And they seem to have a ratio of regular matter to dark matter that's pretty high, or the way it's usually put in the press is that the dark matter is really low. So I think there's more to know about how galaxies form, and there's more to know about the whole range of possibilities. On the average, you know, in the bulk, the presence of the dark matter there's no doubt about it, but in particular places, it may be that those ratios are different. And this seems to be evidence that that's so. So you're right to be puzzled, and these things are not very well known yet. But it does show that there might be more to learn about how the dark matter interacts and how it's connected to the process of galaxy formation. That would be the thing to say, I think.
I have a second question, but might be a little bit dumb, but...
Because that one was awfully good, so on average... You know.
Well, so if we can't see dark matter, does that mean dark matter exists in a different dimension of, like...
Well, it wouldn't have to. It could be just a particle, there are neutrinos, you know, which don't interact very much with matter, but it can't be the neutrino, because we know a little bit about the mass of the neutrino. It's not the right value. But it could be a particle, a subatomic particle, that's not like neutrons and protons and electrons, but sort of another family. So it could exist in our dimensions, but be a different kind of particle that only interacted by gravity.
It's
That's
getting a
what we
little
say.
bit late, so we'll just take the 3 questions from the 3 people who are standing up, and then we'll
I
let
don't know
everyone
much
go.
about this stuff because I'm a microbiologist, but I have a question. Oh, sorry. I say I don't know much about this because I'm a microbiologist.
Uh-oh.
But I
He's
have
setting
one.
me up.
I have one question. Does the cosmological constant, have a dimension?
Does it have a dimension? You mean a size?
No, I don't mean size. I mean, is it energy? Is it mass?
It would be mass energy. It would be, yes. It would be mass, yes. It would be energy. It would be an energy associated with the vacuum.
Because I've read that it is something to do with the oscillation of quantum particles coming in and out of existence.
Yes. Imagine if you imagine the quantum picture of the world on a small enough scale, you would have particles and their antiparticles being created and destroyed all the time. That's the kind of picture of the vacuum that we have. So the vacuum's not featureless. The vacuum's not without properties. But on average, it could have 0 energy and still have those properties. That's the quantum picture. Now, the question is, how does it look for gravity? When you go to the scales, there is a natural scale. Maybe this is what you're asking. There's a natural scale. It's called the Planck length, which is the distance on which these quantum effects for gravity would be very important. And the problem is, the conceptual problem, the intellectual problem, is that we don't have a good quantum theory of gravity that allows us to talk about this in the same way. If you make a naive estimate of what the energy density should be associated with the Planck length and with gravity, it's 10 to the 120th times bigger than the value that we find from this astronomical measurement. So you've put your finger on it. There's a quantitative problem which lies right at the heart of theoretical physics, and for which, at the moment, there's no satisfactory explanation. So there's really something great to do. That guy with the ignorance,
so much.
he was onto something. Right.
Hi, Bob. So if dark matter is everywhere, then presumably it's also part of biology. So how do you see it manifesting itself in living systems such as ourselves? Yeah. And how come we biologists haven't seen it yet?
Yeah. Well, the density is pretty low, and the interaction is very weak. So the idea is that, like neutrinos could go neutrinos from the sun are going right through your body right now, and they're not affecting you because the probability that a particle will hit something as it goes through you is so low that you need a light year of lead, not a meter of water to catch one. You can build devices to see neutrinos, and these are weakly interacting particles. We don't know the interactions that are associated with the dark matter, but they might be something like that. In which case there would be just negligible effects. They don't deposit any energy. They don't do anything to you. So I did a calculation when there was a supernova in 1987. I did a calculation of all the eyeballs of all the people in the world, who would have a flash due to the neutrino interaction. And the answer was 10 people. Yeah. Erwin.
I have a comment first.
Sure.
You're a brilliant talker, brilliant speaker. I loved every minute of it. I have an historical question.
Yes.
Before Hubble discovered the expansion of the universe, two people, Alexander Friedman in the USSR and Georges Lemaitre in Belgium, predicted that the expanding universe was a solution of Einstein's equations without the cosmological constant. What do you know, or what is known, if anything, about whether Hubble was aware of either of their works before he published his paper, which showed the expanding universe and has a graph that has an embarrassing mistake in it?
Yes, I know this. Well, I would say this. I looked into this a little. Hubble, you could see, Hubble was very apologetic about his knowledge of general relativity. He never studied these things. And so I think it was seen by him as something he had to rely on the authority of others. And in 1928, there was an IAU meeting in Leiden, and De Sitter was in charge of the cosmology section, or whatever it was called exactly. Hubble attended that. And there was a prediction. De Sitter had another model, in which there would be a quadratic dependence. That is, there would be redshift would go like the distance squared. And the legend is, and it may even be true, that Hubble, well, it's certainly true that Hubble went to that meeting. It's certainly true that he talked to De Sitter, and that he subsequently came back and told Humason, we better look for this De Sitter effect. So I think what Hubble was looking for was the parabola. What he found was the line. So at least he had the good sense, to only show that and not a fit to a parabola. But and his theoretical underpinnings were very slim, I think. Whereas, as you correctly point out, well, Lemaitre was the one who really understood both the physics and knew the astronomy well enough. And there's, of course, this famous footnote to his French version of his paper about the expanding universe, where he worked out what the ratio of distances and velocities was, the thing we would call the Hubble constant. And Lemaitre worked it out, but using Hubble's data. And there's a complicated story of publication when Eddington, who was the head of the monthly notices, got a kind of interesting letter from Lemaitre who said, I sent you this solution 3 years ago. He did have it published in English, but then without that footnote. And for a while, people thought there was some conspiracy that somehow Hubble had suppressed this. But in fact, Lemaitre is the one who took the footnote out. He said, well, Hubble has better data, and he's shown it more clearly. So I think you're asking a really interesting question that, how much did Hubble understand of what he was doing? And I think it's fairly limited. And the evidence is in his book, I think, where he tells you how hard this was for him, that Lemaitre was someone who had both the physics understanding and the astronomical knowledge. Einstein had the physics intuition, but he didn't really know the astronomy all that well. And so it was a kind of a funny moment where sort of who you were mattered a lot. And the fact that, I think the fact that Lemaitre kind of left the field was something that made a big difference to how people thought about these ideas.
Was Lemaitre at that 28 conference, and did
Good
he
question.
speak?
I don't know, but there is an attendance list. It's in the Harvard College Observatory Library. Is the,
Yeah, I haven't memorized that.
No, of course not. But but you can find the minutes of the meeting. Yeah, I looked it up one time a long time ago.
Fantastic. Well, we have 3 things we have to do. First, we need to thank Bob again. So thank you.